Alright, so today what we're going to do is that we're going to do another applied optimization problem. So this one has to deal with basically a cylinder, okay? So basically the question is asking us, what are the dimensions of the lightest open top circular cylindrical can that holds a volume of 1,000 cubic centimeters? Well, first of all, this looks like basically a lot of stuff is kind of like thrown onto us right now, but let's take it one step at a time. First of all, you have to identify what the constraint is. Alright, so you have to identify what the constraint is. So in this case, the constraint is basically telling us, okay, you can do whatever you want. You can make this as small as possible, as far as like the dimensions, as far as like making it like trying to make the can as light as possible, but you have to do this, right? You have to make sure it meets this criteria. So the criteria it has to meet is that its volume must be 1,000 cubic centimeters. So let's write that out. So the constraint is our volume must equal 1,000 cubic centimeters. So the volume has to be 1,000 cubic centimeters. So that's our constraint. So with that being said, what we're going to do is that we're going to basically have our constraint and we're going to put it inside some equation that basically relates the constraint with some variables. For this case, let me just draw it out for you guys. It's a cylinder. This is our cylindrical can. Let me write it out for you guys. So, cola. It's a Coca-Cola can.
Product placement, y'all.
Wait. I'm sorry, guys. This is copyright. I should do this.
There we go.
A little R.
Brought to you by Coca-Cola.
Right. So, cola. No, that's not Coca-Cola. It's cola.
Oh wait, never mind. Well,
no, it's Speed Cola from like Call of Duty Zombies or something.
whatever.
Why not?
Why the hell not?
Yeah, exactly.
There we go.
All right. So this thing has a radius, R. This thing has a height. Let's call that H. So this thing has a radius and a height. That's basically what matters. But whatever the volume is, it's 1,000 cubic centimeters. So let's write an equation that relates basically relates the volume, the radius, and the height together. Well, obviously we know that the volume of a cylinder is pi r squared h. Well, we already know what the volume is. It's 1,000, so we'll just plug that in for volume. It's going to be pi r squared h. Now for this one, we're actually going to basically solve for one of these variables. I think it's the smartest move to just basically solve for h, so that we won't have to deal with like, taking the square root on both sides. That would kind of be a little bit weird. So instead, we'll just solve for h. Divide both sides by pi r squared. So this pi r squared goes away. So h equals 1,000, all divided by pi r squared. So now this is going to be very helpful because now we're going to go to another equation that relates the idea of the surface area of the cylinder, and we're going to basically use this to help us basically have that equation just in terms of one variable. Okay, that's the idea. So we're dealing with basically making the dimensions of the lightest. In other words, we're taking up the least amount of surface area as possible. That's the idea. And it's also an open top. In other words, that the surface area of a cylinder, that's going to be 2 pi r h plus 2 pi r squared. The reason why you have 2 pi r h, that basically the surface area of like I mean, obviously you know that for a cylinder you have like the top part and the bottom part, but the top and the bottom part are like circles basically. So the stuff that's like in between those circles, that's basically this represents like the surface area of like the pole part of the cylinder.
The circumference of a circle times the height, basically.
Exactly.
To get us like the round.
Right. The 2 pi r squared is basically taking into account basically the area of the circle on the top and the area of the circle on the bottom. So the area of the circle on the top plus the area of the circle on the bottom, pi r squared plus pi r squared is 2 pi r squared. And that's where that 2 pi r squared comes from. The reason why I'm really emphasizing this, because the problem says it's an open top. In other words, we're not including the what's that called? We're not including the top part circle of the cylinder, so we're not taking that into consideration. So the equation of this that we're actually going to use, this is not an integral, by the way. This is going to be 2 pi r h plus pi r squared. In other words, we're subtracting away a circle that was on the top, but it was removed because it's an open top, meaning that the top circled area that's on the top of the cylinder, we get rid of that because it's an open top can. So that looks like an integral, so let me get rid of that. S for surface area. Now that we have this, let's try to take the derivative of both sides. But we can't do that yet because we have this basically this equation here in terms of two variables, and we don't like that. We want this to be only in one variable. So instead of writing h, I'm going to write 1,000 over pi r squared so that we can have all this stuff in just radius, okay, as opposed to just radius and height. So the surface area of this cylinder is 2 pi r. Instead of writing h, I'm going to write 1,000 over pi r squared because that's what h equals to. So 1,000 over pi r squared plus pi r squared. Let's simplify that, right? So the surface area is going to equal, so 2 times 1,000 is going to be 2,000.
Now, if only we could walk away from the rest of the question.
The pi and the pi on the top and bottom, they cancel each other out. So let's write that out. And the r and the r, well, there's an r squared on the bottom. So if you like do a cancellation, you have an r to the first power on the bottom, but then this r just goes away. It's just 1. So now what we have is 2,000 over r on the top, on the bottom. There we go. We have 2,000 over r. Is what I'm saying. And then we have that. We can't really simplify it, so we'll just rewrite it as this. So plus pi r squared. We have the whole thing in terms of r. Now let's take the derivative. So if you take the derivative of s, well, that's just going to be the derivative of s, derivative of the surface area, with respect to r. R is the radius. R is the independent variable that we're taking the derivative with respect to. Okay. Now, how do we take the derivative of this thing? 2,000 over r? Well, 2,000 over r is the same thing as 2,000 times r raised to the negative 1 power. So if you want to take the derivative of that, what that's going to be is negative 1 times 2,000 is negative 2,000. R raised to the negative 2 power, right? Because we're using power rule here. So now that's our derivative for this thing. So it's going to be negative 2,000 all divided by r squared. I put r squared on the bottom because it's r to the negative 2 power, but if you bring it down, the exponent becomes positive. Okay. If you take the derivative of that, you just use the power rule again. Pi is a constant. You don't have to worry about that. So it's just 2 times pi. Well, we don't. Well, pi is like 3.4 or whatever, but just bring down that 2, so it's just 2 pi r. That's our derivative, and we're done. So after we take our derivative, now we take our derivative and set it equal to 0. And we solve for r. What I'm going to do is I'm going to add this negative 2,000 over r squared. I'm going to add it to the other side. So we have this 2 pi r. That's going to stay where it is. And then when we move this negative 2,000 over r squared, when we move to the other side of the equation, it becomes positive. So it's going to be 2,000 over r squared. Now let me write this as 2 pi r over 1. So if you have two fractions that equal each other, you can use cross multiply instead of equal to each other. So 2 pi r times r squared, that's going to be, let me just write down here. That's going to be 2 pi r cubed. And then 2,000 times 1, that's going to be 2,000. I'm going to divide both sides by 2 pi. Boom, that's gone. So now you have r cubed equals, we can simplify this. So 2,000 divided by 2, that's going to be 1,000. So it's 1,000. And then you have a pi that's in the bottom. Then you take the cube root of both sides. So r equals, the cube root of 1,000 is 10. The reason why is because 10 times 10 times 10, right? In other words, like 10 cubed, that gives you 1,000. So the cube root of 10 is 10. and then you divide that by the cube root of pi. So this is what our radius is. Our radius is going to be in centimeters. We don't know what that is, but whatever, it doesn't matter. Now that we have our radius, let's go back to our this thing so we can get the height. So the height equals 1,000 divided by pi times this stuff, the 10 over cube root of pi.
So you can just ignore it for the rest of your calculations. Now you just need to solve
squared.
K.
Man, what's that going to be? Well, you have a 1,000 at the top.
That should be
Now we'll pi out of here. So 10 squared, that's going to be 100.
So now we just need to find, we said that.
And then you have, basically what this means is that when you square the cube root of pi, what's going to happen is that it's going to be,
Ignore this thing.
it's going to be pi to the 2/3 power. Okay. The reason why is because what you have here is pi is raised to the, not negative, but like the cube root of pi is pi being raised to the 1/3 power, and then that is being squared. And what you do is that you multiply the exponent, so that's 2 over 3. So that's what we're going to have here. So pi to the 2 over 3.
Because remember it was.
So h equals, when you multiply this together, it's just going to be 1,000 over, when you multiply the pi times 100 times pi, what you're ending up with here is pi divided by pi over 2/3. So how do we find pi divided by pi over 2/3? When you're dividing this stuff, keep in mind that you subtract the exponents. It's pi to the first power. So let's subtract the exponents. So 1 minus 2/3. What's 1 minus 2/3? You can rewrite the 1 as 3 over 3, because 3 divided by 3 is 1. Minus 2/3, that's 1/3. So the exponent that pi is going to get is 1/3. Or in other words, it's the cube root of pi. So it's going to be 100 times the cube root of pi. And last but not least, we simplify this, right? So zeros go away. And then you just have a 1 on the top. So the height of our Coca-Cola can, I guess, is going to be 10 over the cube root of pi. And then, now that we have our radius in centimeters, it makes sense to have our height in centimeters as well. So what are the dimensions of our So what are the dimensions of our Coca-Cola can? Well, in this case, it's the radius has to be 10 over cube root of pi centimeters, and the height also has to be 10 over cube root of pi centimeters as well. Now, I think it's kind of weird how this cube root of pi, like, basically turned out to be the same thing as the radius. So let me just look back at this and see if I got this right. So 100. That makes sense. Yeah, apparently I got the right answer. I don't think this is wrong. So basically, what's the dimensions? The dimensions means the radius has to be 10 over cube root of pi centimeters, and the height has to be 10 over cube root of pi centimeters as well. Those must be the dimensions of our Coca-Cola can in order for it to have the smallest surface area with an open top, by the way, and keeping in mind its volume is also 1,000 cubic centimeters. And we're done.